Hi everyone. Let's take another look at the amine functional group. So we started in the last video, the last functional group of organic chemistry, amines, and we named them and we did a few reactions with them. We looked at the order of basicity of them. And so now let's look at some new reactions of amines. And then we'll wrap up with going back and reviewing a few more of the reactions that we've seen in the past and get some new insights. Okay, so open up your key concepts, Unit 4, Part 3. First page of that document looks like this, but we already talked about naming, so scroll down, not too far until you see synthesis of amines, new reactions. Now in the other documents, the last document, Unit 4, Part 4, you'll find this graphic describing the SN2 reactions using amines as nucleophiles. And we had touched on this in our last video, right? This should look familiar. We talked about how, where's my pen? Wake up, computer. We talked about how to make an amine. You can do an SN2 reaction. So here's a primary amine. And you can just start with ammonia and take any alkyl halide. So here I'll take 1-bromobutane, and you can do an SN2 reaction to make 1-aminobutane, or this is 1-butanamine. We talked about how to name this. A butylamine would be the common name. And if during a synthesis problem on the exam, you want to make your amines this way, totally allowed. But in the lab, the yields are low and contaminated with higher order amines, higher degree amines, because this product is still a good nucleophile. Nitrogen is a lone pair. And so if you, as the reaction's going, the product is being made, and the product can then attack another molecule of the alkyl halide and produce a secondary amine in this case. Well, I skipped a step, didn't I? I lost a hydrogen here. So you have to add a base to remove that extra hydrogen. 1, 2, 3, 4. In the course of the reaction, other ammonia, other amine can actually serve as the base instead of sodium hydroxide. The problem, the basic guideline here is that, yes, you make amines by starting with ammonia, alkyl halide through an SN2 reaction, but yields are not great. Okay, so there is a need for new reactions to have higher yielding and more pure product. And we have several options here. Here's our first option. And it's actually kind of clever. This next option comes about by analyzing the side reactions here. The side reaction is that your product is still a good nucleophile SN2. So someone said, hey, what if we do pick a new reagent, not ammonia or one of the other amines, so that our product does not form a good nucleophile, and the SN2 reaction can only happen one time. And so then that reagent has to also have to be transformed in some manner to your final product, the amine. Anyways, a good molecule that can perform that is a molecule called sodium azide or sodium azide, NaN3. And if we draw out the N3 molecule, the azide ion, there's 3 nitrogens. And in one resonance structure, you can draw them with double bonds. So nitrogen making 4 bonds is positive. Nitrogen only making 2 bonds is negative. And the net charge here, 2 minuses and 1 positive, is a net -1 charge, right? Yeah, the azide ion or azide ion is N3 minus. Okay, and turns out only one of these nitrogens is nucleophilic, and after it adds, doesn't add again in an SN2 reaction. So step one is go grab your alkyl halide and add sodium azide. And we'll actually just show the mechanism here, because SN2 reactions are one step and two arrows. So pretty quick. Okay, so I'm going to choose this nitrogen. Just going to come back here, strike this carbon, kick out the halide. Halide's a good leaving group. Remember the SN2 reaction? And where the halide used to be, that's where the azide ion now is. Okay, so this nitrogen connects here. It actually makes 3 bonds and it's neutral. This nitrogen is still positive. This nitrogen is negative. There's a total charge of 0. Net charge is 0. And even though this nitrogen is negative, overall, it's not a net negative, and so it's not nucleophilic. Doesn't do another SN2 reaction. So it just sits there. That's your final product after the SN2 reaction. And so we add a new reagent once the first reaction is complete. You add lithium aluminum hydride. And what do you do with every lithium aluminum hydride, every Grignard reaction? Yeah, you add acid, H3O+. Come on. There we go. Lithium aluminum hydride is a reducing agent, adds hydrogens, and you don't have to show the mechanism. Scroll down to see that note. Yep, the memory. On the exam, if I ask you for the mechanism, I'm only requiring the first reaction, not the second one, because we didn't. We'll just don't have to do this one. Adding hydrogens, we'll put 2 hydrogens here, kick this group out, probably as nitrogen with the triple bond or nitrogen gas. So this will be some fizzing happening in this reaction with lithium aluminum hydride, fizzing of nitrogen gas bubbling out of the system. And you'll make your amine in high yield and in fairly good purity. Ooh, and just as an aside, in an airbag system in the car, there's little capsules of sodium azide. It's a salt. They're just in this capsule inside the airbag, and there's a little electronic detonator. That's what it is, a little detonator. And it sets it off, and very quickly, this salt, which is a solid, changes into nitrogen gas, releases nitrogen gas that inflates the airbag very quickly. Okay, so we're not going to do this reaction in the lab because sodium azide can actually detonate on its own. But you have to be careful handling this. It creates a gas very quickly, somewhat explosive. Okay, that's a great way of making amines in high yield, but you can only make primary amines. You'll then have to do another SN2 reaction on this if you want to make it secondary or tertiary or quaternary, if you want to add more carbon to this nitrogen. Okay, there's another method called the Gabriel synthesis, if you like named reactions. And it starts with phthalimide, this molecule here. So I'll draw it over here. Not as neatly as it's drawn there. So you have to start with this molecule. You have 3 reactions also. You begin with sodium hydroxide, common base, and it removes this hydrogen to create a resonance stabilized anion. Let's see, this nitrogen had a lone pair. Now it has 2. And I don't know why I missed. There we go. Negative charge. And if you stare at this a while, you'll understand the acidity of this hydrogen. If we change the nitrogen, to understand why this hydrogen is acidic, just make the change from nitrogen to carbon. And look at this a little while, and then you realize it's one of these beta keto carbonyl groups. It looks very much like a malonic ester or an acetoacetic ester. It's a 1,3-diketo compound, and the alpha hydrogen is acidic in these molecules. And so by switching from carbon to nitrogen, that even makes it more acidic. Why? Because in malonic acid, carbon here is weakly acidic because it creates an anion that gets resonance stabilized by 2 carbonyl groups, more resonance structures, more stable. You also get resonance structures with this carbonyl group and with that one. And it's more acidic because in this resonance structure, carbon bears a negative charge, but now nitrogen bears a negative charge. And nitrogen's more electronegative, and it can stabilize that negative charge better. Okay, a lot of explanation for the first step of 3, but anyways, there it is. Once you remove this hydrogen, nitrogen's negative, it's a better nucleophile for an SN2 reaction. So negative nitrogen will come in and hit this primary carbon, kick out the halide, and then you'll attach the 4 carbons where the hydrogen used to be. That's the second reaction. Third reaction is, what were we after? An amine. What do we have? Well, it's sort of like a double amide. There's an amide up here, an amide down here. It's called an imide on the exam. We want an amine though. So you have to clip or hydrolyze the amides. So you have to do 2 hydrolysis reaction of amides. And we're not going to do it under acidic conditions. We're going to do it under basic conditions, just to keep everything the same. So we started the system, the set of reactions, the Gabriel synthesis, using base. So when we hydrolyze the amides at the end, we're going to keep using base. Okay, so you remember hydrolysis of amides. You can either use H3O+, or you can use NaOH and water. You clip or hydrolyze the amide right here and add a molecule of water. From the water molecule, the OH group goes to the double bonded O, and the leftover H from water. Remember, the OH goes here. This is the OH from water, and the H goes to the nitrogen. And you create an amine and a carboxylic acid. So you can do the same thing here, but you do it twice. You cut up here, make a carboxylic acid to this one. You're going to cut down here, hydrolyze that to make a carboxylic acid down here on the bottom one. And then the nitrogen, it gets cut twice, water adds twice, it's going to get 2 hydrogens, and now you have your primary amine. There you go. And you've seen the mechanism of this in Unit 3, so I won't spend the video time here reviewing that. But you can go back to Unit 3 videos of derivatives of carboxylic acids and look at the mechanism for hydrolyzing amides. Now, to be formal about it, we do need to memorize all those mechanisms, but we've all seen them before, right? So the acid-base reaction, that's pretty straightforward. 1 arrow, 1 step. SN2 reaction, 2 arrows, also 1 step in SN2. And the hydrolysis, darn it, you have to do it twice. but we've seen that before, and it just repeats. Cool. Why is this here? Sorry, that was me cutting and pasting from up here. And then maybe we should go back and reflect. These are very similar reactions. Both of them are producing primary amines. So what's the difference? What's the advantage? Why would you use one instead of the other? Well, if you're making bigger molecules, and let's say over here, you had some other group A, some other functional group, or it's a bigger molecule, has some other atoms in there, and let's see, maybe there's a carbonyl group in here. Yeah, so maybe you have, let's say there's a ketone or something like that. Well, sodium azide will attack the primary halide, but then you have to use lithium hydride, and that'll reduce the ketone. It's like, darn it, maybe you don't want that to happen. So instead of using the sodium azide reaction, use a Gabriel synthesis. And sodium hydroxide will not hydrolyze, what's this called? Hydrate carbonyl groups, but it's reversible. So you can get the reaction, the ketone to survive here. You could start with it here, right? So this could attack, this should still attack the primary. You could have a ketone there. And then the ketone would be over on this end. Let's see, so you got 1, 2, 3, 4. 1, 2, 3, 4, don't want O. And then you hydrolyze, the amide will hydrolyze. This will hydrate. But then afterwards, you remove the water and you get this group back. But then your primary amine might react with the ketone. You might get some other reaction. But the point is that the ketone would survive these reagents, survive this reagent, survive that. Oh, that ketone doesn't see this reagent. Not unlike the sodium azide reaction. So there you go. You would choose between Gabriel synthesis or sodium azide, depending on what else is present in the alkyl halide. Now in the homework, I don't think you see anything in addition to the alkyl halide, so you don't have to worry about it. Cool. Okay, so there's two ways so far, two new ways of making amines, but they both suffer from the limitation that they can only make primary amines. Oh no, that's not true. You can actually use a secondary halide. This one, and I guess you can do it in sodium azide too. Okay, this can still do an SN2 reaction on a secondary halide. And then after you do the SN2 reaction, hydrolyze the product. And then your nitrogen will be connected to where the halide used to be, and I just got myself. That's still a primary amine. Yeah, we're still stuck. Never mind. It's still a primary amine. I'm glad I drew it. Okay. So yes, you're making primary amines in higher yield and in pure, it's a more pure product. But what about secondary and tertiary amines? We still need another way of making amines. So we got this method. It's called reductive amination, not to be confused with animation, making cartoons, animating something. No, we're aminating. Did I say it wrong? Animation. It's making Bugs Bunny here. Amination is where you're making amines. Oh my goodness, by a reduction reaction. Reductive amination. Fun stuff in chemistry. Okay, so what you're going to do is start with an aldehyde or ketone. And you use an amine or ammonia. And in the same reaction, you also add some sodium borohydrate, the mild reducing agent, not lithium aluminum hydride, but the mild one, the one that only attacks aldehydes and ketones, supposedly, the one we talked about before. And you don't have to use ammonia. You can use a primary amine. You can also use a secondary amine, and you can use either aldehyde or ketone with it. Okay, so what's the product of these reactions? Well, they're going to be amines, but how do we understand it? Well, let's review two older reactions from Unit 2. Okay, so let's look at this one. It's an aldehyde reacting with ammonia and sodium borohydrate. So let's split it up. Let's look at the reaction just between the aldehyde and ammonia. And let's look at the reaction between the aldehyde and sodium borohydrate. Now, back in Unit 2, anytime you use sodium borohydrate, you had to follow up with hydronium ion. You had to add acid to finish up the reaction. Okay, so that's a little switch here. But anyways, what does ammonia do with an aldehyde? It forms an imine, which is a nitrogen carbon double bond. So all you do is you replace the O with the N, and nitrogen, keep your carbons. Well, it doesn't have any. And nitrogen makes 3 bonds, so it just keeps 1 hydrogen. What does sodium borohydrate do to aldehydes and ketones? It reduces them to an alcohol. So instead of a double bonded O, you have a single bonded O, and there's a hydrogen. The pi bond goes away. So you're going to do both at the same time. You're going to form the imine, but then sodium borohydrate is going to take away the pi bond. Took away the pi bond and added hydrogen. Take away the pi bond and add hydrogen. You now have a primary amine. But if you start with the primary amine, it reacts, and then I picked a ketone. It could have been an aldehyde. Doesn't matter. The amine reacts with the ketone or aldehyde to form an imine. Let's say I got 4 carbons, and then sodium borohydrate will reduce the imine to an amine. Lose a pi bond, gain a hydrogen. Keep your carbons. And this nitrogen is attached to 2 carbons. It's secondary. What about this one? You start with the secondary amine, add an aldehyde or a ketone, and the first step will be make the imine. And you realize, wait, this nitrogen is positively charged. So won't that form an enamine? Yes, if we didn't have sodium borohydrate. It would go on to form the enamine. That's an M. And the pi bond moves away from the nitrogen. Double bond should be there. There's a trans, you might get cis. Trans would be more favored. But that doesn't happen here because sodium borohydrate would take away the pi bond. That's your final product, and it's nitrogen with 3 groups of carbons. It's a tertiary amine. And yay, we can form any one of those types of amines, primary, secondary, or tertiary. Memorize the mechanism. Memorize the mechanism, but you've seen it before. So just apply what you know. Take the mechanism for making an amine, and right before the end, don't leave it in the amine form. React with the hydride ion of sodium borohydrate. So let's take a look at that. Let's do, I don't know. let's do an aldehyde and the secondary amine. Oh, don't start with an alkene, start with an aldehyde. The mechanism will be the same whether nitrogen has 2 groups of carbons, 1 group, or no groups. No groups, and then it would be just NH3. Okay, the mechanism begins by forming the amine, forming the amine. So we did that by bumping up the pi bond with the nitrogen. Lone pair on nitrogen is good nucleophile. Bumps up the carbonyl group. Whoops. Makes a negatively charged oxygen. Nitrogen adds here, keeps its carbons. There's 4 bonds to this nitrogen, now it's positive. Second step, we talked about this back in Unit 2 that I think the hydrogen can transfer directly. Other chemists think that no, probably another solvent molecule or another molecule of the amine will grab this hydrogen. And then a second step, the oxygen will pull the hydrogen from the second amine. Makes for a longer mechanism, but maybe still a valid one, valid mechanism. But I think this works just fine here. You make an alcohol and an amine. Good, everything's neutral. I hesitate here, think, wait, is it all done? And the answer is no. You're gonna need a double bond to this, and you have to get rid of the OH group. Normally, hydroxide is a terrible leaving group. Not in the aldol condensation reaction. We saw a hydroxy group be the leaving group there. There's our exception. But amines, no, that's not how this forms. We don't lose hydroxide ion right now. Instead, you need to add a catalyst. You had to add an acid catalyst to make your amine. And the alcohol group grabs a hydrogen to change the alcohol group into a disguised water molecule that makes for a better leaving group. So that the lone pair on the nitrogen can come down to make the double bond and kick out the water. And now we have a protonated, or at least a positively charged nitrogen atom. And we release a water molecule that if we're going to the enamine, which is the product of when a secondary amine attacks an aldehyde or ketone, the water would attack this hydrogen over here to create a double bond and create the enamine. But we stop. Now consider the second reagent, sodium borohydride. And in the mechanism, sodium borohydride just donates the hydride ion. And that's a good nucleophile that bumps up the pi bond. And then we're done. There's a hydrogen here. I don't know, do you want to draw it in there? You don't have to. The pi bond turns into a lone pair on the nitrogen. And now nitrogen's happy. It's making 3 bonds, lone pair. There's your product. In this case, a tertiary amine. Nice. And if you want to see how to make a secondary amine, the mechanism, all you do is remove one of these carbons and add a hydrogen. And by doing that, you now have the mechanism to make a secondary amine. Oh, you gotta erase that set of carbons, 2. Cool, so now on the screen, here's the secondary amine. Exact same mechanism, right? Just deleting one of those carbons. And if you want primary, erase the other ethyl group on the nitrogen, add a hydrogen, and it'll make it primary. So now you got the mechanism for all 3 versions. It's the same thing. Cool. Okay, and obviously, I hope it's obvious, out of these three new reactions, the reductive amination is the most useful because it'll make all three varieties of amines, primary, secondary, tertiary. Okay, let's close this and take a look at our last new set of reactions. It's one type, it's called the Sandmeyer reaction. It goes to an intermediate where the nitrogen, there's going to be two nitrogens with a positive charge. That's called the diazonium ion. Because it's a cation, you'll have a counterion. In this case, it's probably nitrite or sulfate. It's probably sulfate. Will be that negatively charged anion of the salt. So if in the homework set, if it says, hey, use a Sandmeyer reaction to create the following molecule, or if it says use diazonium salts to create or to synthesize a certain molecule, then you know it's referring to this series of reactions. Okay, looks a little daunting. There's a lot of stuff on the page. I have to move the page a little bit to squeeze everything in. But let's break this down. It's not as bad as it seems. Okay, Sandmeyer reactions can start from a couple different benzene molecules, but I'll just pick benzene. Okay, and to get to the Sandmeyer reaction, you have to form aniline. So let's review how we did that back in Unit 1. Oh my goodness, we just saw hydrolysis of amides from Unit 3. We saw amines from Unit 2. And now we're going to look at electrophilic aromatic substitution reactions from Unit 1. Chemistry builds on itself. Okay, how do we make aniline? A primary amine connected to benzene. Well, we first did nitration. We had the nitro group. So we had HNO3 with sulfuric acid. And if I want these structures to visually look the same, I'll put the nitro group here, but it could have gone anywhere. And then to change it to aniline, we need to reduce it. And we now have three ways of doing that. So you get the pick. The more troublesome method, not a one, sorry. It's just a hydrogenate. Add hydrogen with your favorite catalyst, maybe palladium over carbon, maybe platinum. And the nitro group changes to the amine. But look out, right? If you have a ketone, an aryl ketone, or a triple bond, or a double bond somewhere else in the molecule, hydrogen and palladium will attack that too. So it would be safer to use the iron and acid in your first step, followed by base. That pretty much leaves everything alone except for nitro, changes it to the aniline. Or the newer one, you can use tin chloride. That's an N. SN is tin with acid, right? Why am I blanking? Let me check my notes. Yes, it's still with acid. Good. It follows the same pattern. A metal with acid, second step base, a metal, but now with chlorine, tin chloride with acid, second step base. And this one's fairly specific for nitro, reducing to the amine. Cool. When I was taking organic chemistry, you use a similar reagent to start the Sandmeyer reaction. So I was taught, hey, switch this 3 to a 2. And instead of adding a nitro group, HNO3 puts a nitro group on a ring, but HNO2 with sulfuric acid changes the amine to the diazonium salt. Let's see, there's 3 here. And this nitrogen has 4 bonds. This nitrogen has 3, it's neutral. That's the N2 group. the diazonium group. Now remember, from Gen Chem, nitrogen gas, the most common molecule in our air, in our atmosphere, was it 78% of air is nitrogen gas? 21%? Something like that is oxygen gas. The Lewis dot structure of nitrogen gas is a triple bond. This is a very stable molecule. So this molecule is a very unstable molecule. This bond wants to break to produce a very stable nitrogen gas molecule. Also gives nitrogen back a lone pair. So there's a lot of driving force. This is very unstable. So you don't have to write it on the exam, but it's important to keep this on ice or colder so it doesn't immediately just decompose on its own. I tell you this because when you're doing synthesis, when you're stringing together your own series of reactions, as soon as you make the diazomium salt, you must pick one of these 6 reactions. You have to do them in order, because in the lab, this molecule is too unstable to maybe I want to add a nitro group here, or do one of the other reactions, or, do some other reaction before I pick one of these. It's like, no, you have no time. The molecule is too unstable. You have to make this and immediately react it. Okay. If you don't do that, if you say, hey, on synthesis dance, I'm going to make this group, and then later I'll put one of these other groups on there. I'm going to do something else with benzene. You will lose points. It's not allowed. Chemistry, nature doesn't allow for that. This group needs to be hit with one of these reagents immediately afterwards. Otherwise, it'll fall apart on its own and do some other chemical reactions. Okay, so what can you do with it? Well, you can put on halogens. We don't have a fluorine analog unless something's been recently found that appeared in the chemical literature, probably has, and just hasn't made it into our textbooks. But for now, you can choose one of our halides, chlorine, bromine, or iodide. And the pattern is bring in the chlorine atom as an acid, HCl, and then you need a catalyst, copper chloride. The copper is in a +1 state. You may not have studied this too extensively, but in general chemistry, you do remember, I hope you remember, that transitional metals are stable at several charges. So copper 1 exists, copper 2 exists, and it turns out the copper 2 ion is more stable than the copper 1. And in this form, you can see that there's one chloride ion, which is a -1. The copper must be a +1. So this is the more reactive form. It's following the same pattern. If you want to put chlorine, if you want chlorine to substitute for the diazonium ion, you have to use HCl with CuCl. And if you want bromine, well, change the chlorines, 2 chlorines to bromines. Cool. And then I would have thought to use this, follow the pattern. Sorry, that doesn't work. You know what? We saw that same pattern before. I think I have it over here. No, it's down here. In a little bit, we're going to review some of those old reactions. There they are. Back in Unit 1, we talked about electrophilic aromatic substitution. And you could choose to put chlorine on a ring with Cl2 and FeCl3. If you wanted bromine on a ring, it was Br2 and FeBr3. And then I was thinking it should be I2 and FeI3. No, we switched it to CuCl2. So iodine was an exception there. And it just has to do with the fact that I2 is a very stable molecule, somewhat reactive. It's used as antiseptic. You may have had grandma disinfect a cutter's scrape using iodine you can buy in a drugstore. Ouch, stings a little bit. But we see the same pattern. Bromine and chlorine have similar reagents. Iodide, you have to tweak it more. We see the same pattern in the Sandmeyer reactions. Chlorine and bromine, same pattern, but then you have to tweak it. It's just sodium iodide, not HI. Okay. For students who need to know, sometimes it's helpful to know the reason so you can remember it. You don't have to know the mechanism for this step here, nor this one over here anyways. But the mechanism involves free radicals. So not on exams. As you have benzene connected to this molecule. And when you add the copper bromide or the copper chloride, it's a +1 ion, and copper wants to be +2. It wants to lose another electron. So it actually donates an electron from copper. This electron from copper leaves, and I'm not really doing a mechanism here, and it adds to the nitrogen, and this bond will break in a second step. Ooh, I should use fishhook arrows, showing that the covalent bond splits. One electron goes to the left, one electron goes to the right. Yeah, it's a free radical mechanism. And you form a halide with a free radical. Ooh, very reactive. This is one of the worst types. But in the process of adding 2 electrons to this nitrogen, you create a very stable nitrogen gas, N2. And the copper is a +2. And then somehow this electron gets transferred back to copper to restore the copper 1 catalyst. And then the bromide goes in place here. It's not a proper mechanism, and that's okay. It's not an exam. All I want you to realize is that you're dealing with free radicals. Iodide actually serves as a catalyst for the reaction. The iodide radical is somewhat stable, definitely more stable than bromide and chloride radicals. This one's somewhat stable. It can form on its own just from sodium iodide. So you don't need a copper catalyst. Iodide, some of the iodide ions actually serve as the catalyst. Anyways, you can also put cyanide on the benzene ring. That's new. And it goes back to the pattern with the little tweak. Sodium was used with iodide. So you can use sodium with cyanide. So it's not HCN. That's a gas. It's toxic. Don't use that one. Sodium cyanide is toxic too, but at least it's not a gas. It's a little safer to use. Just don't eat it. Sodium cyanide, and then you're back to copper cyanide. But it's not HCN, so it's a little tweak. But at least there's a pattern. Cool. You can also change the diazonium salt to phenol, add an alcohol group. So now your reagents have to supply the OH group. Well, that's water. Has the OH group in it. But you need a copper catalyst. So here's a copper 1, but you don't want cyanide or a halide, because if you had that form of copper, copper bromide, copper chloride, copper cyanide, then the cyanide, copper or bromine might substitute for the diazonium salt. So you have to have the oxide. And now I believe the copper 1 oxide is a little bit stable. So you have to add a little copper nitrate to kind of get the system going. 3 reagents that change the diazonium salt to an alcohol, a phenol group, phenol. This one's interesting. You're not using phosphoric acid. That's phosphoric acid. It's not properly a strong acid, but we've seen that acid before, haven't we? Long time ago. Oh yeah. Remember when we're doing electrophilic addition of alkenes? Markovnikov addition, the hydrogen goes to the carbon with more hydrogens, iodide goes to the other carbon. And we said this acid is a very powerful, strong acid, but it also decomposes as it sits in the stockroom. So a better way to do the reaction is to mix some potassium iodide with some phosphoric acid. And these reagents will create hydroiodic acid, HI, to do this reaction. Okay, so we've seen phosphoric acid. I don't want phosphoric acid. Change the 4 to a 2, and you get hypophosphorus acid, I think. Let me check my notes. Or you know what? I should just check the key concepts. It's probably there too. Hypophosphorus acid. Really? OUS, sorry. Oh, here. If you want a name of it, H3PO2, just like we have NaNO2, the twos match, and a hydrogen will go in place. So you actually, it looks like a waste. You started with benzene, did all this chemistry, and then you got rid of it. Turns out it's not wasteful. There's some cool things you can do with diazonium salts, and at the end, get rid of them to put the hydrogen back in place. Cool. Okay, so you need to know these 6 reagents of the Sandmeyer reaction. Put on either one of the halides or a nitrile group, an alcohol group, or just put the hydrogen back in place. You don't need to know the mechanisms. Yes, so know your reagents. A warning again, once you form the diazonium salt, you have to do one of the 6 reactions immediately. Yeah, you must do one of the 6 reactions next. Only arylamines can do Sandmeyer reactions. So I did start to see this on synthesis problems. They thought, ooh, why don't they use an alkane and create a diazonium salt? And no, you can't do that. The benzene ring will resonance stabilize the triple bond here and hold that bond in place through resonance. Without resonance though, as soon as you make this, it immediately, instantly forms carbocation. Oh, right. Both electrons go on the nitrogen to form a lone pair and nitrogen gas. And do we like carbocations? Usually don't. They rearrange and stuff. So don't do this. You only can have benzene on an amine do a Sandmeyer reaction. Oh, and there's no mechanism on the exam. Cool. So kind of as an overview, for unit 4, if you want to put a halide on a ring, you can do it the new way, Sandmeyer, or you can go back and do it the old way. Add your halide group with these reagents too. We have choices. However, the Sandmeyer reaction will give you a way to make nitriles and to put a hydrogen back. There is an old way of making an alcohol. If you had bromine or chlorine on a benzene already, and you had some other metadirector, doesn't have to be nitro, but you had to have this ring deactivated, then you could add base. But you had to have at least one metadirector. You had to have the ring deactivated for this reaction to work. And then you get a substitution reaction. Go back to unit 1 if you want to review the mechanism. But there's a way to make phenols there. The Sandmeyer reaction will allow you to have other groups on here or no groups, and it still works. So the Sandmeyer reaction is superior for making the alcohol group on benzene. This will work, but only in special cases where you have a deactivator present. Cool. Okay. What else do we need to know about amines? Well, let's go back and review some of the stuff we've learned earlier in this semester of organic chemistry and get some new insights. New insights based on the chemistry of amines. So we have these 8 electrophilic aromatic substitution reactions. Of those 8, the most popular for doing organic chemistry, the study of carbon, is to add more carbon. Crafts were the more popular reactions of the set. And they unfortunately had some limitations, right? And those limitations are, hey, you can't do the reaction with vinyl or aryl halides, they had to be alkyl. Had to be sp3 hybridized carbon connected to chlorine or bromine to do Friedel-Crafts. That's the first limitation. Watch out for rearrangements. Yeah, we don't like those carbocations so much. If the ring was too deactivated overall, remember, you couldn't do Friedel-Crafts. Friedel-Crafts shuts down. But the other 6 reactions, they can still work. So adding the sulfonic acid group can still work if you have a metadirector. It's just really slow. Deactivating groups slow down the reaction. But for Friedel-Crafts, it's so slow, it's actually stopped. And here we go. Multistep Friedel-Crafts reactions don't work with aromatic amines. And that was surprising, at least it was for me, because amines on benzene are strong activating groups, right? An amine is your strongest activator. It speeds up electrophilic aromatic substitution reactions. So shouldn't the Friedel-Crafts reactions be the fastest with an amine? And the answer is no. The amine was so reactive, it reacts with the catalyst of Friedel-Crafts, the aluminum chloride. So it actually does an acid-base reaction. The amine with its lone pair acts as a Lewis base and donates a lone pair to the aluminum chloride, which is the Lewis acid, and makes a covalent bond. More importantly, nitrogen then makes 4 bonds and has a positive charge. And that is a feature of metadirectors. The atom attached to the ring possesses a positive charge. I don't know why I put a minus sign there. That's neutral. Here's a minus sign. And the sulfonic acid group, the sulfur has a significant positive charge. And when the atom is slightly positive charge or full positive charge next to benzene, that deactivates a ring. That makes for a metadirector. Nitrogen positive charge now is a metadirector. It's a deactivating group. And now the benzene ring's too deactivated. So it actually falls back on this third limitation. When you have an amine present, it reacts with the catalyst to turn it into a metadirector. And then Friedel-Crafts doesn't work. Even if you add excess aluminum chloride, doesn't work. Okay, and the other limitation for Friedel-Crafts is that once you have the alkane added, once you do the Friedel-Crafts reaction, you create a molecule that's now activated. So now your product can react and make more products, more substituted products. Polyalkylation is the name of that limitation. Okay, let's see. So first thing we saw is a little more explanation as to why aromatic amines don't react. Well, they kind of do, but they don't do Friedel-Crafts because they turn into metadirectors and they react and eat up the catalyst. The other thing we saw back in Unit 1 is that no carbons halides, right? We had to memorize our list of orthopara directing groups. And so amines with a nitrogen and phenol alcohols with an O are no. Those 2 groups, amines and alcohols, are the strong activating groups, strongest. We assigned it a +3 on a point system for how activating the groups were. The second no carbons halides were the amides and the ethers. And then we had our carbons. They can be other chains of carbons or a second benzene ring. Another benzene ring connected to the first one activates it. And of course, this ring then activates the other ring, weakly activates them. That's a +1. The amides and ethers are a +2. If you just have a regular benzene ring, it's assigned a speed of 0. That's what we're measuring all the other reactions against. Benzene has a particular speed of those electrophilic reactions. These activating groups will make it go faster, and the new group will substitute ortho or para. Halides slow things down, but they still direct ortho and para. Okay, so we learned that amines are strong activating groups. And now we're going to fill in a little more details. Turns out in the lab, They are so activating, you don't even need a catalyst. So the other directing groups, for any of those electrophilic aromatic substitution reactions, you need a catalyst. But for like BR2 and FeBr3, if you still write these set of reagents on the exam, you will get full credit. But if you actually go in the lab, you don't have to have the catalyst. The amine is such a activating group, it totally activates the ring to react with BR2 without the need for a catalyst. And in fact, it's so activating, it doesn't stop with adding one of them. So in the lab, hey, chemistry majors, I'm really talking to you guys and gals. If you have BR2 without the catalyst, you think, oh, no catalyst, it's just slow down. Don't we just add it one time? No. Even though you add a halide, which is a deactivating group, right? This is a 3. The amine is so activating, this can react again and a third time with BR2 to get bromine in all positions. That's your major product in the lab. Now again, going back to exams, I'll allow this to happen. Okay. And if you're wondering, what about the other strongly activating group, phenol? It does react with that catalyst. But if you keep the temperature cold, you can just add 1 bromine. It's easier to stop. With aniline, or you have other groups on here and have an amine, you have carbon attached to the nitrogen too. It's still a strong activating group. It's still an amine. It's really hard to stop it with 1 or even 2 halides. 3 is usually your major product. So the amine is more activating than the alcohol group, than phenol. Okay, so chemistry majors, something to be aware of. If you see something in the homework, that's what they're referring to also. Okay, so in the lab, what if you want to make Metabromotolumine? Why is it meta? I'm drawing a blank. Why is an amide used? I'll have to go find out what I'm talking about. I'm drawing a blank why I pulled that out of the key concepts. We'll come back to that because I think it's on the next page. All right, so just to summarize, you should be aware that aniline or any of the amines attached to benzene, if you don't want to add the catalyst, you don't have to. It'll go just fine. But if you leave out the catalyst, you need to know that the halide adds 3 times to all the ortho and para positions. So just avoid that. Just go back on the exams. If you need to do one of the aromatic substitution reactions on aniline, one of the 6 that work, for your craft still doesn't work. You don't leave the catalyst in there and just go back to unit 1. Do it the normal way. Okay, what's some of the other things we need to know about? And maybe that Metabromotolumine will show up here. Okay, we're going to end the video with these 2, synthesizing these 2. These are challenging problems. How do you synthesize these? We're going to map that out in a second. Why are they especially challenging? Well, here's the idea. You're going to start with benzene and make these molecules. So if you start with benzene and decide to do Friedel-Crafts first, put on the ketone group, totally allowed. This is meta director. So the new group has to go here or here. So if you might do the Sandmeyer reaction to add the amine group, not Sandmeyer reaction, sorry, but we saw the Sandmeyer reaction. Oh, that start with the nitro group and then reduce the nitro group to amine. It doesn't work. You can't make the para isomer. You can only make the meta. So then you might say, well, start with benzene and get aniline in place. But now you can't do Friedel-Crafts because aniline is too reactive. It shuts down, doesn't work on Friedel-Crafts reactions. So how are we going to make this molecule? And we have a similar problem here. If you start with benzene, do a Friedel-Crafts reaction to get the methyl group in place, well, that's orthopara. But we want the meta. And you can't add bromine first. Well, you could. But once the bromine's in place, it's also orthopara directing. And we want it to go meta. So that's not going to be the major product. That makes these two molecules especially challenging. But here's the workaround. Sandmeyer reactions and protecting groups. We use the amide group as a protecting group. So lots of ways of making amides. Here you can use an acid chloride, and I know we used pyridine in the past. You can throw that in there too. You can also use excess aniline that can serve as the base. We saw that back in Unit 3. Or instead of an acid chloride, anhydride ester amide, you could use an anhydride. Let's see, what's an anhydride? It's been a while. There we go. Acetic anhydride is the name of that molecule with a low purity. That can make the amide. You can also use a carboxylic acid, an amine, and DCC. And that'll also make the amide. Lots of choices. Pick one, stick with it. And then it turns out, maybe you want to use an acid chloride. The acid chloride will react with the amine first. It's the most reactive. Form the amide. And now the amides, no carbons, halides. Amines are much more reactive than amides. Now if you add the same reagent, but now add the catalyst aluminum chloride, the amide doesn't react. Amines react with this. So in this product, it's benzene's turn. This is going to do a Friedel-Crafts reaction. What kind of directing group is this? Well, when nitrogen connects to benzene as an amide, it's just an activating group, orthopara activating. So we can have the Friedel-Crafts reactions go ortho to the amide or para. And in synthesis, you get to pick the one. In the lab, you're going to make both, and you have to purify it. You have to separate the ortho isomer away from the para isomer that you want. But for synthesis, you don't have to show that. And then, yay, that worked. And then now you hydrolyze it. You could also use base to hydrolyze the amide back to the amine. So cool. That's using protecting group chemistry. Amides work just fine in Friedel-Crafts reactions. Amines, however, don't. So protect the amine from reacting with the catalyst by changing the amine to amide, do the Friedel-Crafts reaction, and then afterwards get rid of the amide group, clip it off. Notice during synthesis that you don't technically have to make this for this reaction because these carbons don't end up in the product. But these carbons, the same molecule, do end up in the product. So you must make this for synthesis problems on exams. And so SOCl2 is your reagent made from the carboxylic acid. And we usually start with alcohols. So start with ethanol and oxidize it with one of the strong oxidizers, maybe Caminone 4. So don't forget to make your reagents for synthesis problems. But if you use a protecting group, realize protecting groups are designed that there's some atoms that go on the molecule and then those to protect something, and then those atoms will come off later. And in that case, you don't have to make it in your synthesis. Save yourself some time. Okay, What was the other molecule? Oh, that's right. This is metabromotolumine. Is that the name of the molecule over here? Yes, yes, it was. Okay, so I got things out of order. Yeah, metabromotoluene. Okay. That's this molecule right here, metabromotoluene. Okay, so we're going to use amide again. Here is the synthesis of metabromotoluene. So how do we get a molecule with two orthopara directing groups situated meta to each other? By using a Sandmeyer reaction. And that clever step at the end using hypophosphorus acid to change the nitrogen to a hydrogen. Okay, this is really clever. It's really cool. What we need to do is, to make this a complete synthesis problem, you begin with benzene and you add the methyl group. So maybe methyl bromide with aluminum chloride. Oh, and synthesis, don't forget, this carbon survives to the end. So you have to make this group from an alcohol, from benzene, from acetylene, you know, the simplest triple bond. What else can you use? Carbon dioxide, I think, is allowed. Take a look at the question on the sample test and see which molecules you can use in synthesis, the ones you don't have to make. One of which are the simple alcohols. Methanol is a simple alcohol. Just change the alcohol group to a halide with PBr3. So to get full credit on synthesis, you need this set of reactions to make this reagent. The reagent reacts with aluminum chloride on benzene to make toluene. Okay, then let's do Sandmeyer reaction. Let's add the nitro group. Well, HNO3, sulfuric acid, will add the nitro group to wherever the directing group says to go. The reagents say what goes to the ring? The directing group says where. Methyl group says, hey, buddy, hey, nitro group, come on over, sit right next to me, or take the head of the table, go para. So in this case, it goes para. We reduce, so you could use the tin chloride, the iron, or you could use hydrogen gas, and palladium. This won't react with it. So any one of those three would have worked. Iron was used here to reduce the nitro group to aniline. Okay, and then what takes that molecule? Well, there's an O with two of these groups. There's a O with a, well, it's not an O. That'll make a peroxide linkage. It's a C with an O and a methyl. And then on this O is this O. And there's another C with an O and a methyl. And wait, this carbon only has 3 bonds. Hey, that oxygen only has 1 bond. Yeah, it's a double bond. Oh, it's acetic anhydride. Acetic and anhydride reacts with an amine. Oh, with pyridine, usually, or the amine could serve as the base to form an amide. Okay. Yeah, and so why? Well, we want to put a bromine on. And so if you would have, in the lab, sorry, on the test, on the synthesis problem, you said, okay, Dennis, I'm gonna start with benzene, start with methanol, make bromomethane, do the Friedel-Crafts reaction, then add nitric acid, sulfuric acid to add the nitro group para, then reduce the nitro group to aniline. If you then said, I want to add Br2, FeBr3 to have the stronger directing group, no carbons halides, that means the strongest. It decides where to go. Hey, bromine, it screams the loudest. Come sit next to me or go to the head table. Oh, wait, you can't sit there. My buddy Methyl's sitting there already, so come sit ortho to me. If you would have done that, you would have gotten full credit. But if you actually try to conduct these reactions in the lab, and you had aniline, you had a Br2 without a catalyst, you get the bromine over here too. We don't want that. So in the lab, you definitely will have to weaken, kind of deactivate the activator The strongest activating group needs to be calm down here. Look, we only want one bromine to go on the ring. So let's turn the amine to an amide and then add the bromine. And then now only one will go in place. The left side or right side, it's the same molecule. Okay, and then now we're going to hydrolyze it. I really do want to see the water here. They didn't put in there because it's basic hydrolysis of the amide back to the amine. And now we do a Sandmeyer reaction. Instead of HNO3 H2SO4, we use HNO2 nitrous acid. This is nitric acid. And 1O makes a world of difference. Using nitric with sulfuric puts nitro group on the ring. Nitrous acid with sulfuric changes the amine to the diazonium salt. Why is there a chlorine here? I don't know. It should be sulfate. I don't know where that chlorine came in here. Let's get rid of it. Yeah, that's weird. I can't think of where that bromine came in. Anyways, I did steal this off the internet. That looks like a typo to me. Anyways, once you make the diazonium salt, you start the Sandmeyer reaction, you got 6 reactions for the next step. Well, what were we after? We're after the Metabromotolumine. We just need to get rid of the nitrogen, add the hypophosphorus acid, and the N2 group will leave and a hydrogen will go in its place. And we made that product. The product we wanted. That was very challenging using older methods of synthesis. Very cool. Okay, I think that's it. Well done. That ends Unit 4. See you in the next video on biochemistry for Unit 5. Take care.